In this video, I'll discuss the quiz questions on Chapter 9. So 9.1 here. Preview. Define energy. Energy is the ability to do work. What's the essential difference between potential energy and kinetic energy? Potential energy depends on the relative positions. Kinetic energy depends on the relative motions. When a baseball moves at 20 meters per second, its kinetic energy is convert 100 grams to 0.1 kilogram. Remember, the SI unit of mass is kilogram. So 0.1 times 20 squared, you get 40, and then divide that number by 2. Because kinetic energy is half mv squared. Submit quiz. Okay, I submitted anyway. All right, 1 out of 3 because I didn't answer the first 2 questions. 9.2. Preview. The first law of thermodynamics: energy cannot be created or destroyed. System and surroundings. System is whatever we study. Surroundings is the rest of the universe. One example that shows the transformation between P and Ke. So if you watched the video of this professor as a human pendulum, its kinetic energy and potential energy are transferred constantly. Nine point three. Delta E is 4.184 joule in the delta E surroundings. Of course, it's going to be the opposite of this number, negative 4.184 joule. Well, I cannot find that number here because look at this. This one is in calorie. But we do know 1 calorie is 1.184 joules. So negative 4.184 joule is negative 1 calorie. Pay attention to the units. When a system does work to its surroundings, what about the sign? Well, if the system does work, it loses energy. Therefore, the sign should be negative. Negative for losing energy, positive for gaining energy. 5.5 joule of heat flows from the surroundings to the system. The surroundings loses energy, so you need to find negative 5.5 joule. I cannot find that number, but over here, 1 kilojoule is 1,000 joules, therefore this number is correct. This is also negative number. The sign is correct, but the unit is wrong. Right, let's see, 3 out of 3. Let's do 9.4. Preview. Delta E is equal to Q plus W, so we put 2 here. Q surroundings is the opposite of Q, so negative 5. Work surroundings is negative work, so 3. All right, submit. Three out of 3. 9.5. Preview. The temperature of an unknown metal increases from 20 to 22 degrees Celsius after absorbing 20 joules of heat. So its capacity, heat capacity is heat divided by the temperature change. So 20 divided by 2, it's going to be 10. Similar question, but we're talking about a specific heat capacity. And if you look at the unit, you probably realize it's going to be heat divided by mass divided by the temperature change. And that's how you do it. 20 divided by 2 over here, the temperature change is 2. 20 divided by 2, and then divided by mass. So 20 over 2 over 20, that's 0.5. The temperature of an unknown substance, 4 grams, increases from 290 to 295 Kelvin, so the temperature increase is 5 Kelvin. After absorbing, well, over here we need to fill in the blank. The specific heat capacity is given. So if you look at this value, you can replace degrees Celsius with Kelvin. 1 degree Celsius is equal to 1 Kelvin if we're talking about temperature change. Again, if we're talking about the change of the temperature, then 1 Kelvin is equal to 1 degree Celsius. And over here, we're talking about the change. So what we need to do is just 4 grams times 5 Kelvin times 0.2. The answer is 4 joules. 3 questions, 3 out of 3. We're done with this one. Okay, 9.6. Preview. Again, this is about heat capacity. The heat capacity is 0.2 joule per degree Celsius. So what's the temperature change? The temperature change is 10 Kelvin or 10 degrees Celsius. So 10 times 0.2, the answer is 2. The temperature of 2 moles of a unknown metal increases from 300 to 310 Kelvin after absorbing this amount of heat. The molar heat capacity is given here. So over here, this is molar heat capacity, and over here we have 2 moles, and again, this degrees Celsius can be replaced with Kelvin. And then it's very simple. It's just 2 moles times 10 Kelvin times 0.3. That's 6. The temperature of 0.2 moles of water increases from 300 to 310. Okay, you have to look up the specific heat of water, which is 1 calorie per gram per degree Celsius. But 1 calorie is 4.184 joule. So you need to convert this to grams. 1 mole of water weighs 18 grams, so this is 3.6 grams of water. Times 10 Kelvin, that's 36. And then times the specific heat capacity of water, which is 8.184 joule per gram per degree Celsius. So again, 3.6 times 10 times 4.184. It's roughly this, 151. 3 out of 3. Number 7. Preview. A gas expands against this pressure. So how do we compute work? Work is negative delta V times external pressure. So it expands, so negative V is 3 liters, positive 3 liters. And then times this 0.6, we get 1.8, but don't forget about the negative sign. Okay, so why is work defined this way? Work is negative delta V times external pressure. This is because when the system expands, it loses energy. So we just define work this way to make sure that when the system does work to its surroundings, the value is negative because the system loses energy. Again, how do we define work and Q regarding their signs? When they lose energy, well, the sign should be negative, right? Okay, now this time we're talking about work surroundings. A gas expands against the surroundings. So actually work is done to the surroundings. This time it's going to be positive, 1.8. Work is, W is negative 1.8 ATM later, but work surroundings is negative work. So it's positive here. Over here, question 3 is about the unit. 1 liter is 10 to the power negative 3 cubic meter, and this is 6 times 10 to the power of 4 pascals approximately. Why did I use pascal? Why did I use cubic meter? Because they are the SI units. So if we look at this number, from 2 to 5, the difference is 3. So it's going to be actually 3 times 10 to the power of negative 3 cubic meter. And then over here, we need to convert ATM to pascals. 1 ATM is 10 to the power of 5 Pascal. So the answer is going to be roughly 180 joules. But don't forget this. The gas expands. It's doing work to its surroundings, therefore work is negative. So negative 180 joules. Here's a trick. 1 ATM times 1 liter is roughly 101 joule or 100 joule. Alright, let's look at this. 3 out of 3, so we're done with this. 9.8. Preview. The change in internal energy of a reaction system is equal to Q under isochoric condition. It's very simple. Delta E equals Q plus W. Isochoric, that means the volume remains unchanged. Delta V is 0. And work is equal to negative delta V times P. So work is equal to negative 0 times external pressure. And work is 0. If work is 0, then delta E equals Q plus work. And work is 0, so delta U equals Q. Question 2. There are 2 blanks. First, we're talking about the internal energy of combustion of this unknown chemical. This internal energy of combustion or enthalpy of combustion must be in joule per mole or kilojoule per mole. So really we just use 24 kilojoule divided by this, the number of moles. We get 1200 kilojoule per mole. But look, this is combustion reaction. The chemical loses energy to the calorimeter. So it's got to be negative. Again, for exothermic reactions, the internal energy of the reaction is negative. For endothermic reactions, the chemical absorbs energy, therefore the internal energy of the reaction is positive. Now the heat capacity of the calorimeter. The calorimeter absorbs this much heat, 24 kilojoule heat. Its temperature increases by 2 Kelvin, so 24 divided by 2, that's 12 kilojoule per Kelvin. Pay attention to the units. 3 out of 3. Let's move on. 9.9. Preview. The change in enthalpy of a reaction system is equal to what under isochoric condition? Well, in this case, it's also Q. Delta H equals Q sub P. So please review the textbook or my video on this topic. Derivation is involved. So, but still, you start from the delta E equals Q plus W. The change of internal energy is equal to Q plus W. You go from there, and enthalpy is equal to the internal energy plus PV, so delta H is delta E plus delta PV. Delta E is Q plus W, and delta PV is P delta V, isobaric condition. And in this case, again, isobaric condition, delta PV is P delta V, and the work is negative P delta V, so these two cancel. In the end, you have delta H is equal to Q under the isobaric condition. The difference between delta E and delta H, by definition, they differ by delta PV. So the change of the product of PV. The enthalpy change of the combustion is this much. Again, it's a negative number because combustion reactions release heat. The chemical loses energy. And we have the number of moles here, and we have the temperature change here. What's the heat capacity? So we need to compute the amount of heat produced by benzoic acid, which is this times this. Okay, so you do the multiplication, you get 16 kilojoule. You want to say negative 16 kilojoule. That's correct, because benzoic acid loses energy. So it's negative 16 kilojoule for this benzoic acid. But where does this energy go? It goes into the calorimeter. So for a calorimeter, it gains energy. It gets 16 kilojoule of heat. So it's positive 16 kilojoule for the calorimeter. And then divided by 2, so I think the answer is just 8. Pay attention to the units. 3 out of 3, so let's move on to number 10. Preview. The enthalpy of this is negative 20, and then we divide every single coefficient by 2, so negative 20 becomes negative 10. Okay, so the first reaction tells you if 1 mole A reacts with 1 mole B and produce 2 moles of C, 20 kilojoule of heat is released. Now we have the amount of every single chemical, then, well, 10 kilojoule of heat is released. Over here, you want to compare this reaction with this reaction. It's just this reaction reversed. You reverse the reaction, you change the sign. So it's going to be 10 here. Done. Now over here, I think I doubled the coefficients, so it's going to be negative 40. And then I reversed the direction, so it's going to be positive 40. So the answer should be positive 40 kilojoule per mole. But my question is about a kcal per mole. So positive 40 divided by 4.184. Okay, submit quiz. Let's look at this. 3 out of 3. So we're done. Number 11. Preview. Oh wow, this is a little complicated, but you just need to just do arithmetic operations for chemical reactions. So for the first question, we just sum up the left hand side. We get A plus 2B plus C on the left hand side. On the right hand side, we have 2C plus 2D. And then the 1C and one of the 2C's cancel. So A plus 2B equals C plus 2D. So really, we just need to add up these two numbers. The result is 10. Okay, over here, this is a little tricky. I don't see any C in this reaction. That means we have to somehow cancel the C's. So we need to multiply this reaction by 2. It becomes 2C plus 2B produce 4D. And this enthalpy of reaction is going to be 60 kilojoule per mole. And then we add up the left-hand side. We get A plus B plus 2C plus 2B. So that's actually A plus 3B plus 2C. On the right-hand side, it's going to be 2C plus 4D. All right? And the 2C on the left-hand side and on the right-hand side, they cancel. And then we just need to have this number multiplied by 2. That's 60 plus this one. 60 plus negative 20, it's going to be 40. Okay, this is also a little bit tricky. We need to reverse the first reaction to put 2C on the left-hand side. So from 2C to A plus B, the enthalpy of reaction is going to be positive 20 kilojoule per mole because we reversed the direction of the reaction. And then we have on the left-hand side 3C plus B together. On the right-hand side, we have A plus B and 2D. The B on the left-hand side cancels the B on the right-hand side. So really we just need to reverse this and then do a addition. Plus 20 plus 30, you get 50. All right, so submit. It's a lot of math regarding chemical reactions. Okay, 3 out of 3, so it's all correct. 9.12. Preview. Bond energy and bond enthalpy, they differ slightly. Because enthalpy is internal energy plus PV. So bond enthalpy is bond energy plus delta PV. That's the change of the product of PV, but that's usually negligible compared to the bond energy or bond enthalpy. So we're going to say differs slightly. The difference is often negligible. This is covered in one of my lecture videos. Alright, over here, since the difference is negligible, so bond energy and bond enthalpy are used interchangeably. Alright, over here, if you look at this reaction, you need to break the AB bond. How do you break a bond? You need energy. How much energy do you need? You need 200 kilojoule per mole energy. So you need to absorb 200 kilojoule, but over here you release 400 joule. In total, you release 200 joule. Exothermic. Oh, by the way, none of the chemical reactions is a nuclear reaction. Okay. In a nuclear reaction, you need to change actually the number of protons in the nucleus. Alright, over here, oh, this is complicated. You need to break AB bond and CD bond. So you need to absorb this much heat. You need 800 kilojoule per mole heat. So 800 flows in. And then when you form the AC bond, 400 flows out. When you form BD bond, 500 flows out. So 800 flows in, 900 flows out, overall 10 flows out, negative 100, negative 100. All right, let's see, 3 out of 3, we're done. Okay, let's see. Okay, we have 2 more, 13 and 14. So 9.13 first. Let's do a preview. Oxygen air is in force. It's only 0.2 atm or 0.2 bars approximately. For a gas to be in the standard state, the pressure of the gas or the partial pressure of the gas in the mixture has to be 1 bar. That's not 1 bar. It's not even close. It's only 0.2 bars or 0.2 atm approximately. Enthalpy of reaction from A to B is 50, and you reverse it. Of course, it's negative 50. Okay, you reverse the reaction. You change the sign for enthalpy of reaction. Okay, from A to B is 50, then from 2A to 2B is 100. So 100, but the reaction is reversed. So again, these two are a review because many students didn't do well in the previous quiz, so these 2 questions are designed for you to review these topics. When you reverse the reaction, you need to change the sign of the enthalpy of the reaction. And also when you double the coefficients, you need to double the enthalpy of reaction. If you double the coefficients and reverse, you need to double this number and then put a negative sign in front of it. Therefore, negative 100. Submit quiz. 3 out of 3. So let's do 1 more. Preview. Wow, this is very complicated over here, this question, but first I want to remind you one thing. The definition of electron affinity is wrong in the textbook. The electron affinity of fluorine is supposed to be positive according to UPAC. But unfortunately the textbook is wrong. It gives you negative 330. So, but anyway, the meaning is the same. Over here, it takes 420 kilojoule per mole energy to remove an electron from potassium. And then if you add an electron to a fluorine atom, it will release 330 kilojoule per mole of energy. So that part is correct in the book. It's just the definition of electron affinity is wrong in the book. Alright, so that's why I give you this equation, the correct equation here. This is how electron affinity is defined. it's reversed in the book. I would encourage you to Google UPAC and electron affinity to see the correct definition of electron affinity. Alright, so the enthalpy change of this. It takes 420 kilojoule per mole energy to remove an electron from potassium, but now it's reversed, so I'm going to find negative 420 here. Alright, and then look at this. What we're doing is we're looking at this following minus losing an electron. So let's look at this definition here. The enthalpy change is the enthalpy of fluorine minus the enthalpy of fluorine minus the enthalpy of fluorine minus the enthalpy of fluorine minus. So that's indeed the electron affinity. So I'm gonna put 330 here. So over here negative 420, over here positive 330. Negative, positive. All right. Now over here, question 2 is a follow-up. So basically, this equation is the sum of this and this. So what you need to do is just sum up these two numbers. You get negative 90. So over here, it's exothermic. It's an exothermic reaction because again, this is a negative number. I think this is also a follow-up. You have solid, gas, ampersand means and 1/2 equals 0.5. The ionization of potassium is this much. The electron affinity is given. So really what we can do is we can compute this. But we're not done yet. How do we compute the lattice energy of ionic compound Kf? So we also need to know how this is being formed. This is being formed from solid potassium and fluorine gas. So we need to look at that over here. So potassium solid and the fluorine gas. All right. Let's see. Also here. So we have this. Oh, and over here too. 1, 2, 3. So these three answers contain that critical equation from solid potassium and fluorine gas to this ionic compound. We need this equation. Okay. So the last answer is wrong for sure. And now one more thing. Over here, this equation tells us this K plus in gas phase plus F minus in gas phase can form K atom in the gas phase and fluorine in the gas phase. We need to somehow relate this potassium atom in the gas phase and the fluorine atom in the gas phase to the normal states of potassium and fluorine, which is solid potassium and the gaseous fluorine molecules. So only this one connects the potassium in the gas phase to potassium in the solid phase. This equation connects the fluorine atom in the gas phase to the fluorine molecule in the gas phase. Again, potassium is in the solid phase typically. Fluorine is in the form of molecule in the gas phase, so we need this too. And then we react the potassium solid with fluorine gas to produce this ionic compound. 3 out of 3, so we're done.